Hi, I'm Dennis, and I'll be talking about the Novo Mesto meteorite fall. I'll be talking about the trajectory, orbit, and fragmentation analysis that we did from daytime optical observations. At 10:30 in the morning of February 28, 2020, people in Slovenia, Croatia, Hungary, Austria, and Italy saw a bright fireball in the sky which fragmented into many pieces. In southeastern Slovenia, people reported hearing a loud explosion and rumble shortly after the fireball. It was also observed by many security and dash cameras, as you can see in these videos. Three meteorites from 50 to 470 grams were recovered by locals within 2 weeks, and they were very quickly put into labs and analyzed. The meteorites are L5 chondrites that are strongly shocked, they show dark melt veins, and are virtually pristine because of the very quick recovery. Because of the high shock stage, most chondrules are fractured and displaced. The meteorites are brecciated and composed of several different types of clasts in fine grained matrix, as you can see on the image on the right-hand side. The next important thing is to derive the trajectory on the orbit and to put this rock in a solar system context. So it's like getting a free sample return mission such as Hayabusa or OSIRIS-REx. Now, we would usually calibrate on stars, but because it happened during the day, we simply couldn't do that. So we used the edges of buildings, windows, signposts, or distant mountains as something to hold on to. We sent people to take DSLR photos of these points of interest from accurately known locations. And those photos also included stars, and this allowed the images to be very accurately calibrated. And by combining these different images and observations of those points of interest from several locations, we were able to triangulate their locations to a precision of a few centimeters. On this slide, you can see an example of 2 points of interest. They're marked with red crosses as seen in the dashcam video. That's on the left-hand side. And on the right-hand side, you can see the 3 calibration images. You can see some stars in the distance, and at the top, you can see their locations. Next, we projected those points onto the dashcam video frames and used them to calibrate the lens distortion and the camera pointing. You can see the used points as green markers in this video. And on the right, you can see that we even used the elevation profile of a distant mountain chain for calibration. We also had to invert the location of the camera on every video frame to an accuracy of a few centimeters. Now, note that some of the vehicles were traveling over 70 kilometers an hour, but it was important to do so to get a high degree of measurement accuracy. The astrometric fit errors on every video frame were around 3 arc minutes for most observations. Combining observations from all stations, we computed a trajectory. The trajectory fit errors were within 100 meters for nearby stations and about 300 meters for the distant observer in Italy. Together with dashcams, we also used 3 fixed security cameras in southern Croatia, which were significantly easier to calibrate and give credence to this trajectory solution. The fireball was first observed at the height of 69 kilometers, and it was last visible as 17.3 kilometers moving at around 5 kilometers a second. The very deep penetration into the atmosphere and the high speed at the end indicate that the final observed fragment was very large. We estimate that the final mass was on the order of at least several kilograms, but it was never recovered. It probably fell into soft ground as the predicted fall zone is over farmland, and it was thus plowed over before we had a good estimate of the full location later in the year. The wind measurements were taken 1.5 hours after the fall and only 65 kilometers away, so the strewn field matches well to the finds. The right-hand side image shows the strewn field for rocks ejected at the end point for a range of masses. The only inconsistency is along the trajectory location of the 2 smaller meteorites. They probably began their dark flight prior to the end point and thus fell behind the main mass. The location of the largest 469 gram piece is consistent with endpoint injection. We support this scenario by the fact that a mass-sorted fragment train was directly observed by one of the cameras, as we will discuss on one of the next slides. The fireball was also observed seismically. The main fragmentation was heard by 8 nearby seismic stations. The cylindrical ballistic wave, which propagated behind the fireball, was heard by only one station, so it couldn't be used to constrain the trajectory, but it is consistent with the optical solution. Seismometers also possibly observed the precursor waves, which are formed when the air wave hits the ground below the fireball, couples with the ground, and produces weaker seismic waves which propagate faster through the ground and reach the seismic stations before the air wave. Here we present the preliminary trajectory and orbital solution. Due to the COVID-19 measures, we only very recently obtained DSLR calibration images for 2 additional dashcam videos, but we don't expect these numbers to change significantly. The orbit is what is to be expected for an ordinary chondrite and does not stand out. By utilizing the criteria, we found a possible connection to several near-Earth asteroids, but that remains to be confirmed through numerical simulations, as this orbital parameter space is densely populated and such connections are often spurious. The stated errors on this slide were computed by adding 3 sigma noise to the observations and recomputing the trajectory solution using a Monte Carlo approach. We found that adding only 1 sigma errors often does not reproduce the real uncertainty when simulated data is used. In a future paper, we will also determine the source region of the meteorite to pin down the delivery mechanism of L chondrites to Earth. To derive the initial mass of the meteoroid and the fragmentation behavior, it is necessary to measure its energy deposition in the atmosphere, which is usually done by measuring the light curve. Light curves are traditionally calibrated on stars, which was not possible in this case. Fortunately, the total radiated energy of the fireball was observed by US government sensors and published on the CNEOS website. Assuming a luminous efficiency of 7.5%, as appropriate for a meteoroid of this speed and large mass, we scaled the relative light curve measured from one dashcam. Furthermore, we purchased one original dashcam that observed the fireball and derived an absolute calibration using a light source of known brightness. For this, we imaged the reflection of the sun off of a chromium sphere at various distances and simulated the range of magnitudes between -15 and -24. Both these approaches produced very similar results as visible on the left-hand side image. We then scaled the relative light curves from other cameras and matched the calibrated one to produce a complete light curve. We were then able to fit the semi-empirical meteoroid ablation model to the observations. The bulk density of 3,200 kilograms per cubic meter, as appropriate for chondritic meteorites, matched the observations well. We derived an initial mass of around 4 tons. The body had several fragmentations between dynamic pressures of 2.6 and 11.6 megapascals, but lost most of its mass, around 90%, at the fragmentation which occurred at the height of 35 kilometers and 3.4 megapascals. The fireball had a fragmentation profile similar to other ordinary chondrites, but the first round of expected fragmentations above the height of 70 kilometers, around 0.1 megapascals, was not observed directly, as the fireball was too dim at the time. Nevertheless, a wake at the beginning was indicative of a prior fragmentation. The main body survived dynamic pressures of up to 12 megapascals, one of the highest ever recorded for a meteorite dropping fireball. On this slide, you can see the fragmentation progression of the meteoroid. At the point of the largest fragmentation at 35 kilometers, the meteoroid ejected a significant amount of dust, which remained luminous for several seconds, and the main body fragmented into 17 distinctly observed fragments. Some fragments showed a large lateral offset from the main trajectory. As only 3 fragments were recovered, and they were not the largest according to the dynamic mass measurements, the rest should still be present underground. In a future work, we will make accurate measurements, derive the mass distribution, and compute strewn fields for individual fragments. In conclusion, using the Novo Mesto meteorite dropping fireball as a case study, we developed a new method of calibrating dashcam and security camera videos of fireballs. The method can be applied to future cases with relative ease through the open source software we made publicly available. We also developed a new method of photometry calibration for daytime fireballs, which can be done on a shoestring budget, assuming that one original camera which observed a fireball can be obtained. Finally, we'd like to state the importance of obtaining the original security or dashcam footage, as YouTube or other sites' compression algorithms can severely degrade the video quality, even though it might not be initially obvious.